This work presents a deep learning-based outlier rejection method for non-rigid point cloud registration. Our main motivation is to leverage the local rigidity of non-rigid deformation. To this end, we first introduce a local spatial consistency metric based on the deformation graph built over the source point cloud to measure the geometric compatibility between non-rigid correspondences. On top of this, we inject the local spatial consistency metric into the self-attention mechanism and further design a graph LC net to classify non-rigid correspondences to inliers and outliers. Experiments on fold image have proved that our method can eliminate more outliers while preserving more inliers. In this work, we propose a deep learning-based outlier rejection method for non-rigid point cloud registration. To our best knowledge, this is the first learning-based non-rigid outlier rejection method. Outlier rejection is a common technique for robust point cloud registration. However, most existing methods focus on rigid registration. The most commonly used method is ransack. It randomly samples a small set of correspondences to generate post-hypotheses, and then selects the best hypothesis among them. However, non-rigid registration requires dense and thoroughly distributed correspondences to precisely describe the deformation, thus preventing the application of sampling consensus methods. On the other hand, spatial consistency-based methods are another popular class of methods. It measures the compatibility of two correspondences by the discrepancy between the respective distances in two point clouds. Given two inliers, for example, x1, y1, and x2, y2 on the left, their spatial consistency sit1, 2 should be close to 1. But if there is an outlier, such as x3, y3, the corresponding spatial consistency should be 0. However, in non-rigid registration, the global spatial consistency does not hold anymore, especially between two inliers far from each other, such as x1, y1 and x3, y3 on the right, because the points in different parts of the scene could follow inconsistent movements. To address this issue, we propose a novel local spatial consistency metric to measure the geometric compatibility between non-rigid correspondences. Our main motivation is to leverage the local rigidity of non-rigid deformation, which means the local structures of point clouds tend to be preserved after being deformed. Our method is based on the deformation graph built over the source point cloud. We first sample a set of sparse graph nodes on the source point cloud via uniform furthest point sampling, and assign each correspondence to its key nearest nodes. Then we define local spatial consistency between two correspondences which are assigned to the same node, as in the equation on the right. Compared with the global spatial consistency, our method can effectively measure the geometric compatibility between non-rigid correspondences within a local region. The local spatial consistency between two inliers are likely to be close to 1, while the value should be 0 if there is an outlier. Based on the local spatial consistency, we then propose a graph-based spatial consistency network, a graph LC net for short, for non-rigid outlier rejection. Given a set of putative correspondences, graph LC net leverages the graph-based local spatial consistency to remove the outliers from them. The core design here is the graph-based correspondence embedding module. After generating the initial features, it first collects the correspondence features around each graph node, and then extracts spatial consistency-aware correspondence features by injecting the local spatial consistency metric into the self-attention mechanism. Afterwards, we aggregate the features from all assigned nodes for each correspondence as the final features. At last, a classification head is adopted to predict the confidence of each correspondence being an inlier. Extensive experiments on folding match have proved that GraphLC has achieved the new state-of-the-art non-rigid registration performance and significantly outperforms the baseline outlier rejection methods. And the visualizations have shown that our method can eliminate more outliers while preserving more inliers than existing methods, such as point DLC. Furthermore, our method shows strong generality to unknown datasets, such as KEEP and deep deform. To summarize, our main contributions are as follows. First, we propose the first deep learning-based outlier rejection network for non-rigid point cloud registration. Second, we design a graph-based local spatial consistency metric to measure the geometric compatibility between non-rigid correspondences. Third, we introduce an attention-based correspondence embedding module to extract spatial consistency-aware correspondence features. Thank you for watching. Our code and models are released at GitHub.